In section 6.5, we're going to learn how to use U substitutions and a change in variable to integrate some functions that would be difficult otherwise. So before we start, let's look at three derivatives using the chain rule. So if I look at this first example, if I were to take the derivative of the sine of x squared with respect to x, I know that I would take the derivative of the outer function, so the sine function, and get the cosine of x squared, and then I would have to multiply that by the 2x, the derivative of the innermost function, and that's just the chain rule. So the derivative of sine of x squared is 2x times the cosine of x squared. All right, pause the video and take the other two derivatives real fast. Hopefully we remember our derivative rules, and using the chain rule, for number 2, we should get 3 cosine of 3x, and for number 3, 21x squared cosine of 7x cubed. So it stands to reason, if we understand the relationship between the derivative and the antiderivative, that means that if I take the antiderivative of 2x cosine of x squared, that I should in fact get the sine of x squared plus c, my constant of integration. The same is true in number 2. If I take the antiderivative of 3 cosine of 3x, we should get the sine of 3x plus c, the constant of integration. And lastly, the antiderivative of 21x squared times the cosine of 7x cubed, we would get the sine of 7x cubed plus c as the antiderivative. So the purpose of using U substitution is to be able to find an antiderivative when we are working with a function that has that is a derivative by the chain rule. So back to page 90 of our spiral, we've already talked about the text up top. So we're gonna do some examples, and when we get to the example that I starred, we're actually going to look at that through the lens of a definite integral as well. So we're going to apply the integration techniques that we learned earlier in this unit with U substitution. The first thing is we need to figure out what U will be equal to. And because these are functions that could result from the chain rule, we want to set U equal to the inside or innermost function. So when I look at the function or the expression 2x times e to the x squared, e to the x squared is a composite function. It's e to the power of something, so it's an exponential function with a base of e, where that something is a function of x. So I'm going to let U be x squared. To figure out what du must be, we will take the derivative of u equals x squared with respect to x. So I'm going to take the derivative with respect to x of both sides of the equation. And typically we won't show this work, but just for this first example to understand how we get du, let's look at it. So on the left, if I take the derivative of u with respect to x, that's implicit differentiation since u is not x, and we get, well, du dx. And I'm going to write it in this notation. On the right side, the derivative of x squared with respect to x is just 2x. And so for us to solve for du, to isolate du, we're going to multiply both sides by dx. So what we are left with is du equals 2x dx. Okay, so these are the two equations, u equals x squared and du equals 2x dx. We're going to need these for our substitution. So if I look at my original integral, I'm just going to rewrite it to the side a little bigger. I should be able to identify what is u. So my u, which is x squared, is just the x squared. And I should also be able to identify du. So we said du is 2x times dx. And remember that dx, that represents the infinitesimally small width of each rectangle when we use the Riemann sum and we take the limit as the number of rectangles approaches infinity. So dx is being multiplied with 2x e to the x squared. All right, so if I replace everything that I highlighted, I'm going to now have e to the power of u, and my 2x dx gets replaced with du. So now I have an integrand that represents or is represented by one of the formulas that we learned earlier in this unit. So I know that the antiderivative of e to the something is e to the something plus c. So now that this is a du, we're going to take the antiderivative with respect to u. So we're not using the variable x right now. So we get e to the u plus c. So lastly, if we are asked to find the antiderivative of 2x e to the x squared dx, we need to rewrite this in terms of x. So once we get this antiderivative, I'm just going to go back and substitute for u my x squared. So my final antiderivative is e to the power of x squared plus c. And if we take the derivative of that, we should get 2x e to the x squared. All right, let's look at another example. So again, we want u to be the inside function. And when I look at example 2, the innermost function that I see is x cubed. And if I think about it, the derivative of x cubed is 3x squared. So that is a big hint that I've chosen the correct u because du I can see in my integrand. All right, so I'm going to let u be x cubed. And instead of showing all the work where we take the derivative of u equals x cubed with respect to x on both sides, I should just be able to see that when I take the derivative on the left, I'm going to get a du. The derivative of x cubed with respect to x is 3x squared, not cubed. And then we'll have our dx on the right side. So that's what we need to perform our substitution. We've already identified u in our integrand, and my du is 3x squared dx. So my 3x squared and my dx will be replaced with du. So when I rewrite my integral in terms of u, I still have the secant squared. We didn't substitute anything for the secant function, but now it's the secant squared of u, and the 3x squared and the dx gets replaced with du. So now we use our antiderivative rules. We know the antiderivative of secant squared of u is the tangent of u plus c, the constant of integration. And again, that's just from, I think that was section 6.5 6.1 actually, 6.1. Okay, so last step is we're going to take the tangent of u plus c, and we're going to do the final substitution back to x cubed, and that becomes the tangent of x cubed plus c. And that's our final answer. All right, the next example, I want us to look at the indefinite integral, but then we're going to go out to the side and look at what happens when we do use substitution with a definite integral, and that will help you in some of the practice problems that we associate with this unit. Okay, so first of all, when we have a fraction, it might be hard to figure out what u is, but if I look at that, I know that I need a du in my integrand as well. So I don't want 2x to be my u, because then du would just be 2. However, I see the expression x squared minus 3. And so if I use that as my u, then du will be 2x. So I want that whole thing for u. So u is x squared minus 3. So when we take the derivative with respect to x, we get du is 2x minus 0, so just 2x dx. So I can see my du and my u in my integrand. So it might help me, because I don't really want du sitting on top, it might help me to rewrite this initially as 1 over x squared minus 3x, nope, minus 3, sorry, just minus 3, times 2x dx. I think looking at it that way will help us see what rule we need to use when we take the antiderivative. All right, so if we perform our u substitution, we're now looking at the antiderivative or indefinite integral of 1 over u. And the 2x dx is now a du. So 1 over u, I know that's my natural log because it's u to the first power. So my antiderivative will be the natural log of the absolute value of u plus c, the constant of integration. And then lastly, we're going to substitute x squared minus 3 for u. All right, so out to the side, I want to look at what happens when we're working with a definite integral instead. And so I have the same example, but I went ahead and gave it limits of integration. So e squared and e to the 5th power are the limits, and that's what makes this a definite integral. So this is the same example we just looked at. So we said if we do our u sub, that u is this junk on bottom, du is the 2x dx, and oops, see if I can zoom out. We already know that we've got 1 over u when I do the u sub. So we have two choices here, and usually I'll tell you what I think is the easiest. So you might notice that over here I left off the limits of integration. So if I write them in terms of x, these original limits, e to the 5th and e squared, were limits for when my definite integral is written in terms of x. So in other words, they're x values. So e to the 5th and e squared. However, they're not u values. So for my definite integral, if I want to write my limits, I need to rewrite them in terms of u. So for my lower limit, I'm going to substitute e squared in for x. So e squared squared minus 3, that becomes e to the 4th minus 3. So that's my lower limit, e to the 4th minus 3. My upper limit, so u of e to the 5th, would be e to the 5th squared minus 3. So that's e to the 10th minus 3. Okay, so those are our new limits of integration. And when we do a u sub, we have the choice to change our limits of integration. And here's why I think it's easier. So we said no matter how we do this, we're using the natural log rule. So I could either write my antiderivative now as natural log of u. And remember, when we have a definite integral, we don't need the plus c, but I could evaluate this from e to the 4th minus 3 as my lower limit and e to the 10th minus 3 as my upper limit. Or I have the choice to do the u substitution. So I could go back and substitute for u x squared minus 3 and evaluate this for my original limits in terms of x. Now, I don't know what's easier. I think often leaving it in terms of u is easier, but either way, the math is going to be the same. So if I evaluate this definite integral in terms of u, that's what's on top, I'm going to have the natural log e to the 10th minus 3 is a positive number, so the natural log of e to the 10th minus 3, and then that would be minus the natural log of e to the 4th minus 3. And like from there, I'm not going to go through all of the log rules, but we could rewrite that using log rules. On bottom, if I plug this in, I'm going to have the natural log of e to the 5th squared minus 3 minus the natural log of e squared minus 3. So we get the same thing either way. Oftentimes, though, it's easier to leave your antiderivative in terms of u and to rewrite your limits of integration as values of u instead of x. But one way or another, you're going to do the same math. So when you're working on any of the practice problems for this unit, and it's a definite integral and not an indefinite, if you use these original limits of integration, you need to do your substitution back so that your antiderivative is in terms of x. Or your other choice is to run these through your statement where u equals something in terms of x and get new values, new limits. Okay, that was my aside. All right, this last example for this page, and then we'll move on to some more challenging ones. The last example, I'm going to have to rewrite this either way, so I'm going to do it in the beginning. I don't have an integration rule for a radical, but we do have an integration rule for a power. So really, our integrand could be written as the product of two powers. All right, so if I look for my innermost function, that's going to be my x to the 4th plus 3. So I'm going to let u equal x to the 4th plus 3. When I take the derivative, my du is going to be, I'll take the derivative of x to the 4th for x cubed. The derivative of 3 is 0. And remember, this gets the times dx. So that's what u equals, and this is what du equals. So if I look for my du, it's 4x cubed times dx. So I have u to the 1/2 power, this is all my u, and everything else is my du. So this is really just the power rule. My antiderivative, I'm going to add 1 to my exponent, and then I'm going to divide by my new exponent, which is 3/2, and that's the same as 2u to the 3/2. Ooh, I forgot my plus c. Sorry, 2u to the 3/2 over 3 plus c, our constant of integration. And so lastly, we could substitute back our expression for x. So that is 2 times x to the 4th plus 3 to the 3/2 power over 3 plus c, the constant of integration. So as far as u substitutions go, these examples show us some pretty basic or straightforward u substitutions. And the way that I know these are basic or straightforward is that my du is exactly as I want it to be in my integrand. The next series of examples on page 91, we will have to do a little bit of a manipulation with a constant multiple to generate the du that we need.